All right, welcome to our Master Jedi lesson. Have you ever wondered when an elite volleyball player executes a jump serve, how they convert a slow high toss into a fast downward hit over the net? Or does the ball magically just gain energy mid-air? Or is it transforming energy from one form to another? Today, we're going to answer that question. In a world without friction or air resistance, energy can never be created or destroyed, only transformed. But every bit of kinetic energy in a booming serve comes directly from the mechanical energy input of the toss, the swing, and the work done by the player. So, to just draw a little diagram of that, we have a person tossing a ball into the air. So it goes up, and then after it gets tossed, he runs forward, jumps, so he's in the air now, and he's hitting the ball over a net. And then it lands on the ground or into a server's hand or a receiver's hand, and we were trying to figure that out. With that, we're going to be talking about the law of conversion of mechanical energy. And for our variables in units today, we're working with mass because we got to figure out our mass, and that is in kilograms. We're also figuring out the height of how high the person is in the air when they hit the ball. We're talking about acceleration as well, velocity, and energy. So our mass is in kilograms, our height is in meters, our acceleration is meters per second squared, our velocity is meters per second, and our energy is in joules, which can be kilograms times meters squared over seconds squared. So, a player tosses a volleyball, which has a mass of 0.27 kilograms, straight into the air with an initial upward velocity. So our initial velocity is 7 meters per second. From the release height of 2.0 meters. Using the conversion of energy, we're going to find the maximum height the ball reaches at its apex, where velocity is going to end up being 0 meters per second. We already know what acceleration is because that equals 9.81 meters per second squared. So we are going to calculate our mechanical energy. For our calculation of our energy, that's going to equal kinetic energy plus potential energy. For our kinetic energy, the formula for kinetic energy is 1/2 mass times velocity. And that is going to equal 0.5. Our mass is 0.7 kilograms. And our velocity is 7.0 meters per second squared. Sorry, I forgot to add. It's 1/2 mass times velocity squared. When we add all those up, we're going to do 0.5 times 0.27 times 49, because 7 times 7 is 49. It's going to equal 6.615 joules, because that's what our energy converts into, because it's kilograms times meters squared over seconds squared. We are also going to figure out our potential energy. And potential energy equals mass times acceleration times height. That's what we are figuring out. So that will equal 27 kilograms, 9.81 meters per second squared, and our height is 2.0 meters. That equals, after we do our math, 0.27 times 9.81 times 2 equals 5.297. I'm going to put that in green just so that we can see what our numbers are. That one is also in joules because we have our mass, kilograms times meters squared, because we have 2 meters right here, as we multiply over seconds squared. Then, because we are working with our original formula up here, our mechanical energy equals kinetic energy plus potential energy, we are going to add those two together. So 6.615 joules plus 5.927 joules. 6.615 plus 5.927 equals, did I do the math right? Oh, no. Not 927, 297. We're just gonna rewrite that. 297. So 6.615 plus 5.297 will equal 11.912 joules. Now we are trying to find the maximum height using conversion of energy. So at the very top of the toss, the velocity of the ball. So when the ball reaches all the way up right before it's about to fall down, so once it's at its very, very top, it equals, velocity equals 0 meters per second. So if that's the case, then the kinetic energy of the ball when it's at its max peak after tossing it into the air equals 0 joules. All mechanical energy is stored as potential energy. So the energy when it reaches its max equals the potential energy when it is at its max. And if all of that equals the same, our energy will then equal 11.912 joules So now that we have our baseline, now that we have how much energy is stored up into this ball when it reaches its max height, when it's tossed into the air, we are going to figure out how high the ball is going to be at its apex. So in order to figure that out, we're going to use the formula of our potential energy of our final is going to equal mass times gravity or acceleration times the max height. We're just going to do height m for max. Because that equals 11.912, this right here, this guy, I'm going to underline it in blue just so we can keep track. The potential energy of our final equals this guy right here, 11.912. So now we have to figure out what our numbers are throughout here. We have our mass, 0.27 kilograms. We have our gravity, which is 9.81 meters per second squared. But we don't have the height of the ball. So we're trying to figure that out. In order to figure this out, we're going to multiply these two variables together. Our 0.27 times our 9.81, which is going to equal 2.6487. We're just going to round it down to 3 decimal places. So these two multiplied together equal 2.649. We'll just do that. But in order to get the height that we are looking for on its own side, we have to divide our potential energy by our new number. So our potential energy, 11.912 over 2.649 equals the height at our max, and that will ultimately equal 4.5 meters. So when the hitter jumps and spikes the ball at its apex of 4.5 meters, they do external work on the ball, which transferring their muscular chemical energy into kinetic energy. If the hand swinging does 115 joules of the work on the ball during impact, so when he's in the air swinging, so he's swinging with his hand right here onto the ball, if he's putting 115 joules of energy into the ball, the mechanical energy that is exerted within this hit right here rockets from 11.9, because it gets all the way to the top, it gets hit so hard that you add those two together, 115 plus, let's just say 12 because it's 11.9, we can round that up, which equals 127 joules, launching the ball forward at whatever speed you calculate from there. So, to finally wrap this up, every jump serve is really just a lesson in energy conversion. The upward toss trades kinetic energy for height. Gravity stores it as potential energy, and the hitter's swing adds a massive burst of work, transforming stored energy into the high-speed kinetic energy that slams the ball across the court. Thank you so much.